Hey everyone, and welcome to the channel. I'm Vic, and today we're kicking off a series that I'm incredibly excited about. I called it A Beginner's Guide to Hardware Software Code Design, building a Linux-controlled hardware accelerator on the Zynq UltraScale Plus SoC. We're going to be diving deep into the world of modern embedded systems. Now, if you've ever wondered how companies create incredibly high-performance devices, things like smart cameras, advanced networking gear, or even the control systems in a modern car, the answer often lies in a powerful technique called hardware-software code design. It's a fascinating topic that sits right at the intersection of electrical engineering and computer science. And over the course of this series, we're going to demystify it completely. This is going to be a full, hands-on beginner's guide. We'll start with a blank slate and walk through the entire professional workflow, from designing a custom piece of digital hardware to building a tailored Linux operating system for it, and finally, writing a software application that can talk to and control the hardware we just created. Our platform for this journey will be the incredible Zynq UltraScale Plus MPSoC from AMD. Specifically the Zynq development board. It's a beast of a platform, but by the end of this series you'll understand exactly how to tame it. So whether you're a student, a hobbyist, or a professional looking to get into FPGAs and SoCs, you're in the right place. Alright, so before we start writing code, let's talk about the fundamental concept here. What is code design and why is it so important? The simplest way to put it is that code design allows us to get the absolute best of both the hardware and software worlds. Let's break that down. First, you have the hardware, which I like to call the muscle. In our case, this is the FPGA or programmable logic portion of our chip. Think of an FPGA as a massive sea of building blocks that we can wire up in any way we want to create a custom, high-performance circuit. Because this circuit is physically built to do one job, it's incredibly fast and efficient. This is what we call hardware acceleration. It's perfect for tasks that are highly parallel or need to happen with very precise timing. Things like real-time video encoding, complex signal processing for 5G, or running an AI model's calculations. For our project, we're going to start with the most basic building block of a digital logic, a simple calculator circuit called a half adder. But raw power isn't enough. You also need intelligence, and that's where the software comes in. It's the brain. Our chip has a powerful multi-core ARM processor, the same kind of processor you might find in a high-end smartphone. We can run a full-featured operating system like Linux on it. This gives us access to a massive ecosystem of tools, libraries, networking stacks, and file systems. It allows us to make complex decisions, serve a web interface, or communicate with other devices over a network. It provides a level of flexibility that would be impossible to achieve in pure hardware. Co-design, then, is the art and science of partitioning a problem. We identify the performance critical parts and build dedicated hardware accelerators for them in the FPGA fabric. Then we use the processor and the Linux OS to manage those accelerators, feed them data, and handle all the higher level logic. The software decides what to do and the custom hardware does it fast. And the device that makes this powerful synergy possible is the Zynq UltraScale Plus MPSoC. That's a mouthful, but MPSoC just stands for Multiprocessor System on Chip, and it perfectly describes what it is. It's an entire powerful computer system integrated onto a single piece of silicon. If we look at the high-level diagram of the chip, we can see the two distinct domains we just talked about. On one side, you have the processing system, or PS. This is the brain half. On our chip, this includes a 64-bit, quad-core ARM Cortex A53 application processor. This is a serious CPU, more than capable of running a responsive Linux desktop environment. It also has other processors for real-time tasks, but we'll focus on the A53 cores for this series. Then, right next to it, you have the programmable logic, or PL. This is our muscle. It's a vast, flexible fabric of FPGA logic gates, memory blocks, and specialized signal processing slices. It's our blank canvas where we can instantiate our custom Verilog or VHDL designs. But here's the crucial part, the real magic of the Zynq architecture. These two halves aren't just glued together. They are connected by an incredibly high bandwidth, low latency communication fabric right on the chip itself. This means our software running on the ARM processor can read and write to our custom hardware almost as if it were just another part of its own memory. This tight integration is what enables the true potential of co-design, giving us performance that would be impossible if the CPU and FPGA were separate components on a motherboard. Okay, so how do we actually build something for a platform this complex? We need a suite of powerful, professional-grade tools. First up is AMD Vivado. This is the Integrated Development Environment, or IDE, for the hardware side of things. It's a massive piece of software where we'll do everything from writing our Verilog code to synthesizing it, which is the process of turning that code into a physical configuration for the FPGA's logic gates. We'll also use its block design feature to visually connect our custom hardware IP to the Zynq's processing system. Next, and this is a big one, is the PetaLinux Tools. Building a custom Linux distribution from scratch is an incredibly complex task that could take months. PetaLinux automates this entire workflow. We feed it our hardware design from Vivado and it builds everything we need: the bootloader, the Linux kernel, and a complete root file system, all perfectly configured for our specific hardware. A key part of this process is generating the device tree, which is a special file that essentially acts as a map telling the generic Linux kernel exactly what custom hardware peripherals are present and where to find them. Now, here's a key point. The PetaLinux tools must run on a Linux operating system, specifically a distribution like Ubuntu. If you're not running Linux natively on your development machine, you have a couple of options. You could use a local virtual machine with software like VirtualBox, or you can do what many professionals do and leverage the cloud. For this series, I'll be using an Azure Virtual Machine. Setting up a powerful Linux VM in the cloud is surprisingly easy and cost-effective, and it gives us a clean, robust environment to run our PetaLinux builds without cluttering our main PC. It's a great way to access the necessary compute power on demand. Finally, once the OS is built, we'll use a standard C++ code editor. You can use AMD's Vitis IDE or something like VS Code to write our final user space application. This is the program that will actually run on our embedded Linux system and control our hardware. And the physical board that brings this all to life is the AMD Zynq U3. It's a fantastic and cost-effective board for learning. As you can see, it's packed with features. At its core is the Zynq U3 EG MPSoC. Supporting the processor, we have 8 GB of fast DDR4 RAM, which is essential for running a full OS. For I/O, it has everything you'd expect from a small computer: USB 3.0, Gigabit Ethernet, and even a mini DisplayPort for video out. And most importantly for us, it has a great set of built-in peripherals for us to start with, like these push buttons, slide switches, and LEDs. These are perfect for our initial Hello World style tests. Finally, it has a ton of expansion ports like PMODs and a Raspberry Pi header, opening the door to countless future projects. Alright, that's the grand tour of the what, the why, and the how. We've covered the theory, the platform, and the tools. And finally, before we move on, if you're interested in this kind of content or want to connect professionally, feel free to look me up on LinkedIn. I'd like to connect with fellow engineers, students, and enthusiasts in this field. It's time to get our hands dirty. In the next section, we're going to fire up Vivado and begin designing the hardware heart of our system.